Hi everyone. So today we'll be discussing on the topic Gomory-Hu tree, right? So this is one of the well-known algorithms actually, right? So let's go on with the same. Gomory-Hu algorithm is the algorithm that converts the undirected weighted graph into the tree, right? It converts what does it convert? It converts the undirected weighted graph into the tree that preserves all the pairwise minimum cuts. Yep. So just remember this. For any two vertices u and v, we should be having more than this one vertex, right? So for any two vertices u and v, the minimum cut value in the original graph equals the minimum edge weight on the path between u and v, right? So again, let me read this one out loud. Just listen to this carefully. For any two vertices u and v, these two vertex that we are considering, the minimum cut value is nothing but the original graph uh, in the original graph equals the minimum edge weight on the path between u and v in the Gomory-Hu tree. Yep. So it reduces big of n square minimum cut computations to only big of n minus 1 maximum flow computations. What it does, it reduces the big of n square minimum cut computations to only big of n minus 1 max flow computations. Just remember this. So this is one of the important things. Let's move on with the key idea here. So instead of computing minimum cut for every pair of vertex or every pair of vertices, we build a tree where each edge stores the minimum cut value. So that is the reason here. Mainly this one. It reduces the time complexity from big of n square to big of n minus 1, right? So this is the main advantage of using the Gomory-Hu tree, right? Just remember this. Yep. Again, instead of computing minimum cut for every pair of vertices, we build a tree where each edge stores a minimum cut value, right? So the minimum cut of u and v, nothing but the edges. The minimum cut u comma v is equivalent to the minimum edge weight on the path between u and v in the tree, right? So this is the key idea. So we'll discuss the approach now before writing the code. So this is the main idea actually. Just remember this one, right? So we'll be implementing the same thing by considering the example. Yeah, let's discuss the approach. Let's do that. So yeah, let me do one thing. Let me maximize this one. Yeah. So just give me a second here. What happened to this one? 1 second. So I'll do one thing. I'll show the approach here itself. See, we'll be considering this particular graph. Yeah. So we'll be considering this particular graph with a vertex 1, 2, 3 as well as 4. Just give me a second here. So you can clearly see here we are having 4 vertices or the 4 vertex, individual vertex, right? So 1, 2, 3, 4. So we will be going with this particular example. So edge weights you can clearly see between 1 and 2. For 1 and 2, this one edges we have the weight 3, and for the edge 1 to 3 we have the weight 2. This one, yeah. Next for the edge 2, 4, this particular one we have the weight 4, and for the edge 3, 4, for this particular one we have the weight 1. Yep. Next let's move on with the algorithm steps. First what we'll do, we'll choose the root here, right? So we will be choosing the root. So we will be picking, or what we'll pick first, we'll pick vertex 1, this one. Yep. We'll pick vertex 1 as root. So parent array initially will be parent of 2 will be 1, parent of 3 will be 1, and parent of 4 will be 1 as well. So 2, 3 as well as 4. These for these three things actually, this one, what do we call? Parent will be 1. All other nodes, you can say, for all other nodes, the parent will be 1. Next step will be we have to compute minimum cut of this one. Accordingly with the key idea, we have to compute minimum cut of 2 comma parent of 2. Then we will compute minimum cut of 2 comma 1. Parent of 2 is nothing but 1. So we have considered here minimum cut of 2 as well as parent of 2 1. So it will be 1 here. 2 comma 1 using the maximum flow. So the result will be minimum cut, we will be getting 3, right? So after getting the minimum cut, right? So then what we'll do, we'll split the vertices into 2 sets. What we'll do, this step is very important. We will split the vertices into 2 steps. Yep. So as we get here, nothing but the first vertex that we get here. The first vertex we get here is this one 2 comma 4, and another one, another edge will be 1 comma 3. So these two things, right? So we have successfully split the vertices into two sets. The first set, sorry, not the first vertex or the edge. So here the first set is nothing but 2, 4, and the second set would be 1, 3 respectively. Now after the second step, let's move on with the third step. Nothing but so before moving on with the third step, so we have to update the parents for the vertices in the S for this one. Yep, 2, 4, whatever we have considered the first set. So we will be, what we'll be doing actually, we will update the parents for vertices in S, right? So we will compute min cut of 3, parent of 3. Parent of 3 is also 1, right? So for the vertex 2, 3, and 4, the parent is 1, right? So we have already discussed this one. So we have to compute min cut of 3 and a parent of 3. So it will be minimum cut of 3, 1, right? So the result will be 2, the max flow. The result will be 2. Now let's get into the partition part this time. So for previously, for this particular one, when we consider 2, 1, we have split the vertices into two sets, 2, 4 and 1, 3. For this, we will be splitting this one into two sets, nothing but this one. What do we call? 3, 4 as well as the 1, 2 respectively. Yeah, two sets 3, 4 as well as 1, 2 respectively. So next we have to compute min cut of 4, parent of 4. Parent of 4 is also 1. For the node 2, 3, 4, the parent is 1 itself, right? So again we have to compute the minimum cut of 4, so this time it will be 3. Sorry, I got confused here. So parent of 4 will be 3 accordingly. So here also I mentioned the same. See here. So here parent of 4 directly we have 3. 3 then 3 to 1 we have, right? So it will not be 1. So change this one. Yep. Parent of 4 will be 3 actually, not 1. So this is fine, I believe. Yep. So here we are computing the minimum cut of 4 and parent of 4. So computation I have showed. So minimum cut of 4, 3. So min cut we will be getting 1. Min cut we will be getting 1. So overall, we have done the same thing for 2, 1, 3, 1 as well, and 4, 3, right? So the output that we got here, we can clearly see here. For the first one, we got 3 minimum cut. For the second one, we got the result 2, 3, 2, as well as for the third one, nothing but 4, 1 edge, we got the minimum cut 1 respectively, right? So edge we can represent in this way. For 1 to 2, it is 3, and for 1 to 3, it is 2, and for this one, 3 to 4, it is 1, right? So final Gomory-Hu tree we can just represent in this way. Just please pause the video and have a look into it. Yeah, I insist you to pause the video and have a look into it. You'll get it easily, right? So for 1 to 2, it is nothing but the weight would be 3. For 1 to 3, the weight would be 2, and from this one, 3 to 4, the weight would be 1 respectively. Just now we discussed the same thing. So this is it for the approach. So the minimum cut of 2, 4 is equivalent to the minimum edge on the path. What is the path actually? It is from 2 to 1, 1 to 3, and 3 to 4. 2 to 1, this one. I have shown you the tree actually. Yeah. So 2 to 1, then you can clearly see here 1 to 3. Yeah. Then finally 3 to 4. So that's what 2 to 1, 1 to 3, 3 to 4. That is the reason I have clearly shown you the tree here, this part. Yep. It's as simple as that. Now we are done with the uh, approach part actually. Yep. So minimum of 3, 2, 3, 2, and 1 is nothing but 1. Yeah. Min of 3, 2, and 1 is nothing but 1. Yep. So this is it for the approach. Next, what we will be doing, let's do one thing. Now we have the idea, right? We have discussed the approach. We had discussed the key explanation as well, the key idea, right? So that one also we had done. And now we are left with only two things, nothing but writing the code and discussing the complexities for the code that we have written. Yep. Let's do those two things. So let's do one thing. Let's start writing the code. So one more thing, I have already shown you the graph, right? So we'll hard code the same example within the code, right? So let me show you the graph once again so that we don't get confused. Yeah. So one thing, so this will be the graph 1, 2. So this was 4 actually, and this will be 3, and this one weight will be 3. This is 4, 2, and this will be 1 respectively. You can just pause the video and have a look into it. Yeah. So we'll be going with this particular graph. Right. So now let's do one thing. Let's start writing the code. Just give me a second here. Yeah. So first thing, the number of vertices in the graph was 4, right? So I'll just go with the static here, int. So vertex, I'll just consider 4. So this is fine. Next, let's go with the capacity matrix representation. So let me do one thing. Let me go with static here. Also, let me go with int. I'll just consider the capacity, or I would have written cap. That was also fine. One second. What happened here? Let's type this one again. So I'll just go with the capacity here. So this will be new int of vertex v as well as v respectively. Yep. Next, what I'll do, let me go with a. So we have to go with a parent array. We have to make use of the parent array to build the Gomory-Hu tree. That we have to do. We know this, right? So let's go with static here. We'll just go with int. Let me go with a variable parent. So this one will be new int of. We'll just pass the vertex v. Vertices, nothing but v, the variable that we have considered. Finally, we have to store the minimum cut value for the each vertex. For that, I'll just consider the variable cut value. Yeah, I'll just go with static here, int. So let me go with cut value equals new int of. Let me pass v here again. Right, so these are some of the global variables that we'll be making use of. Next, what I'll do, let's go with a BFS. Actually, we'll be making use of the BFS for this. Let's go with a BFS that we'll be using to find the augmenting path in the residual graph. Yep. So let me go with static here. Just go with Boolean. So let me go with the BFS. Just go with a this one parameter s. Just go with the t, which is of type int, and also let me go with a parameter parent flow, and finally let me go with the parameter residual. Yep. So this is fine, I believe. So within the BFS method, first thing, we need the visited array for the BFS travel, quite obviously. So I'll just go with Boolean here. So let me go with visited equals new Boolean. Let me pass the vertices, nothing but variable v. So this is fine. Next, we need q, right? As we are making use of the BFS, we'll be making use of the q, quite obviously, right? So I'll just go with q of integer. So this is fine. Let me go with q equals, sorry, yeah, I'll just go with new. Let me go with a linked list here. Let's make use of the linked list. Yep. So this is fine. Then so we have successfully made use of the queue. Next, we have to start the BFS from the source vertex, right? So in our case, whatever the example that we have considered, or in the approach that I showed you, right? So the source vertex was 1. We are having the nodes 1, 2, 3, 4. The source vertex or the source, this one node is nothing but 1, right? So I'll just go with q dot add. Yeah, I'll just pass the source vertex s. Right. Next, we have to mark the source as visited. For that, I'll just go with visited of s. This one, misspelled visited. Let me correct this one. Visited of s. Let me set this one to the Boolean value true. So this is fine. Now, let's go with a standardized BFS loop. Nothing but while loop. So I'll just go with while of not q dot is empty while the queue is not empty. Then let's proceed with the further things. First thing, we have to remove the next vertex from the queue. For that, I'll be making use of the word this one variable u. I'll just give here q dot poll. So this is fine, I believe. Next, we have to check all the vertices for the possible edges as well. For that, I'll be going with a for loop, simple for loop. Yeah, I'll just go with for in v equals 0. I'll just go with v less than v. I'll just increment the v. So this is fine. Yep. So within the for loop, I'll just go with a simple if condition, because if the vertex is not visited and the residual capacity exists, in that case, we have to move further. For that, we have to write the simple if condition, right? For that, I'll just write here. See, I'll write in this way: if not of visited of v, and I'll just go with a residual here. This one residual of u and v. So the edge u and v itself, right? Yeah, u and v. If it is greater than 0, then what we need to do, we have to store the parent for augmenting path. For that, I'll just make use of the variable parent flow. We have already declared this one. So I'll just go with a, let me assign this one to the U. Next, we have to mark this particular vertex visited. As we have visited, we have to mark this one as visited, right? For that one, I'll just go with visited. So this is fine. Visited of V. Let me set this one to the Boolean value. It's as simple as that. Yep. Yeah. Next, we have to add the vertex to the queue. For that, I'll just go with a queue dot add of vertex V. It's simple. Now let's move on with one more if condition here, right? So if the sync is reached, then the augmenting path is quite obviously found. For that one also we have to write the this one, what do we call the simple if condition, right? So that's one of the important edge cases as well. So I'll just go with if v equals p, then quite obviously in that case we have to return Boolean value true. Yep. So this is fine, I believe. This is it for this one. Yep. Else no augmenting path will be existing. So in that case, we have to return false. Let me give here return false. Yep. So this is fine. This is it for the this one BFS method. We are done with the BFS method successfully. Let me come out of this one entirely. Let me format the code so that this looks good. Yep. So this is fine, I believe. Next, what we'll be doing, let's go with a Edmonds-Karp algorithm. So if you don't know Edmonds-Karp algorithm, we have already discussed this one. So it is present in the 150 algorithms playlist. You can just have a look into it and later you can come back, right? So the main focus is on Gomory-Hu tree rather than the Edmonds-Karp algorithm, right? So now we will be making use of the Edmonds-Karp, this one algorithm. So I'll just go with one more method here, static int. I'll just go with max flow. Yeah. So I'll just go with S, your parameter T, and let me go with Boolean here. Yeah. So I'll just go with the parameter reachable. Yep. So this is fine, I believe. So within this particular method, max flow method, so we have to go with the residual capacity graph. For that, I'll be making use of the variable residual here, right? So I'll just go with a residual. Yeah. So this one will be new int of, let me mention v as well as v respectively. Yep. So this is fine. After going with the residual capacity graph, so we have to copy the original capacity matrix. To copy the original capacity matrix, I'll be going with the two for loops. Yep. So let me go with for here. So this one will be int I equals 0. So I less than v, and let me increment the I as well. Yeah. So let me go with one more for loop here. So this one will be j equals 0, j less than v. Let me increment the j. Yeah. What happened here? Yeah, I have misspelled int. Let me remove y here. Yep. So this is fine. The final thing is we have to copy the original capacity matrix, right? So for that one, I'll just go with a residual. So this one residual of I and j. So I'll just assign this one to the capacity of I and j. Yeah, you would have already guessed this one. It's as simple as that. Now, yeah, let's move on with the further things. So we have to go with the total flow value. Let me initialize the variable flow with a 0. Yep. So this is simple. Next, we have to store the augmenting path as well. For that, let me go with the parent flow here. And let me assign this one to this one, new int of b, right? So this is fine. One second. So yeah, let's continue with the same. So now, let me write the simple while loop here. So while this one augmenting path exists, then only we have to move forward. So that is the reason I'm making use of the while loop here. So I'll just go with a while. So let me call the BFS. We have already written the BFS method here. So I'll just call the BFS method here. So this is fine. Let me pass st, the parameters, right? St. Let me go with a parent flow as well. And finally, let me go with a residual as well. Yep, it's as simple as that. Now, within the while loop, what I'll be doing. So let's go with a bottleneck capacity of the path, nothing but here in this case, I'll be making use of the path flow variable, right? So I'll just go with path low. So I'll just go with a positive infinity, nothing but here in this case, integer dot max value, right? So this is fine. Yep. So let me one capital F. Yep. So this is fine. Next, after going with the bottleneck capacity, so let's do one thing. We have to traverse the path backwards, right? So we have to traverse the path backwards. For that, I'll be making use of the for loop, right? So I'll just go with int vertex v. I'll just assign this one to t, v not equal to s. Then let me assign v to this one, parent flow, this one, not path flow actually, it's parent flow of, let me pass v. Yep, so this is fine. Then within the for loop, what we have to do, just give me a second here. What we need to do, all we have to do is we have to traverse the path backwards and we have to update the bottleneck capacity, right? So let me assign you to parent flow, not the path flow, sorry, just give me a second here. Parent flow of v. Yep. So here, and one more thing, let me consider path flow. Path flow, let me, we have to update the bottleneck capacity. For that, I'll just go with math.min here, right? So I'll just go with path flow. And also let me pass here. We have to go with a residual, right? So I'll just select this one and we have to pass the edge, nothing but u and v vertex, right? So this is fine. We have successfully updated the bottleneck capacity. Now let me come out of the for loop. So I'll just write one more for loop. I'll just tell you why we will be making use of one more for loop actually. Yeah, we have to update the residual graph capacities as well, right? So for that we need one more for loop. So let me write it on this way. So I'll just go with for int v equals t, v not equal to s. So I'll just assign v equals parent flow, this one, of v. Yep, so this is fine. So within the for loop, again, this time we have to reduce the forward capacity, we have to increase the reverse capacity, as well as we have to add the path flow to the total flow. These three things we have to do within the for loop. It's as simple as that. First, what shall I do? I'll just go with int u equals, let me call the parent flow here, this one, parent flow of v, right? So this is fine. Next step is, as I've said, we have to reduce the forward capacity. For that, I'll just go with residual here, residual of vertex u and v equals residual of the same edge minus path flow. Yeah, let me make use of the path flow. Same thing, I'll just go with residual of this one. This time it will be v and u. So what is this actually? Why we are writing again? So we have reduced the forward capacity. Now we are increasing the reverse capacity. To increase the reverse capacity, we'll be going with v and u, right? Respectively. We'll just go with same thing. Let me call the path flow here, right? It's as simple as that. So finally, we are left with only one thing, nothing but we have to add the path flow to the total flow, right? So we have to add the path flow to the total flow. For that, what I'll be doing, so I'll just come here. So let me go with flow equals flow plus path flow. Yep. So this is it for the coding part. So this is it for the coding part. And let me come out of this one entirely. Let's continue with the further things actually. Yeah. Now we have to find the reachable nodes, right? So to find the reachable nodes, uh, we have to mark the nodes as visited. Whatever the nodes that we have visited, we have to mark that one so that we don't have to visit that one again, right? So I'll just go with Boolean here, visited equals new. Let me go with a Boolean here. Let me pass the vertex. Sorry, v. Yeah, vertices. Basically, we are storing in the variable v, right? So let's go with a q again. Yeah, I'll just pass the integer here. So what happened? Yeah, let me go with the integer. I'll just go with new linked list. Yep, let me make use of the linked list. So this is fine. Now again, the same thing. I'll just go with the q dot add of s. Let me go with visited. This one I don't have to explain the BFS part again, I believe. Right? Let me type this one quickly. Yeah. Now let's go with a standardized BFS loop again, right? So I'll just go with, I would have copy pasted the same thing actually. Let me type this one anyways. Yeah. So I'll just go with while of not Q shouldn't be empty, right? This is the standardized BFS loop actually. Yep. So this is fine. 1 second. Yeah. Within the while loop, what I'll do, I'll just go with in Q equals Q dot all. Yeah. This one I'll not be explaining again. So I have already explained this one within the this one BFS method, right? So I'll just go with int v equals initially 0, v less than v. Let me increment the, yeah, within the for loop, the same thing. The if condition here, if not of visited of v, and again let me go with a residual here, the vertex u and v. So if it is greater than 0, yep, the edge actually. Here, what we are doing, we are checking for the this one, whether the vertex is reachable or not. Yeah, this is nothing but the reachable vertex condition. I can just put it in that way. Yeah, within this if condition, let me go with the visited of v. So let me assign this one to the Boolean value true. So this is fine, I believe. Finally, we'll be adding this one q dot add of v. Yep, so this is fine, I believe. So let me come out of this one entirely. Now let's go with a very simple for condition. So why we will be going with a for loop here? So let me tell you this one. We have to store the reachable side of the cut. We have to do this one. We have to store the reachable side of the cut at any cost. So I'll be going with one more for loop. So I'll just go with for here int I equals 0. So this one I less than v. So let me increment the I. Yeah, so within the for loop, what shall I do? Word of braces, I believe. Anyways, I'll just write it directly here itself. Let me go with the reachable here, reachable of I. Let me assign this one to visited of what? Visited of I as well. Yep, so we are done with this part. Finally, we have to return the minimum cut value. So we have to find the minimum cut itself, right? So we have to return the minimum cut value at any cost. So for that, I'll just go with return low. Yeah, let me give your return low. Yeah, I'll just come out of this one entirely. Now we have to build the this one Gomory-Hu tree, right? So we have to build that one. So let me come out of this one entirely. Let me make use of one more method, namely build tree. Yep. So I'll just go with static here, right? So let me go with void. I'll just go with a build tree. Yep. So this is fine, I believe. So within this particular method, so I'll do one thing. So let me go with for loop. We are going with a for loop because initially all the vertices have root as parent. So this one we had discussed on the approach itself, right? So for the node 2, 3, and 4, the parent was 1. Yep. So we are building the tree now. So I'll just write the for loop in this way. See, I'll just go with int I equals 1, I less than v, and let me increment the I. Yep. So I'll just go with parent of I. So let me assign this one to 0, right? Why am I assigning this one to the 0? Because as I have said, initially all the vertices have a root as parent. Yep, this one we have discussed on the approach as well. Let's move on with the further things, man. I'll just go with a one more for loop here. So I'll just go with s equals 1. So I'll just go with s less than this one. What do we call? S less than v, and let me go with s plus plus. Yeah. So within the for loop, what I'll be doing, let's go with the parent node first. So I'll just go with the equals parent of s. So this is fine. Next, so we have to store the partition of the minimum cut somewhere. For that, I'll be making use of the variable reachable, which is of the type Boolean. Yeah. So let me go with reachable here. So this will be size v. Yep. So this is fine. Next, we have to compute the minimum cut using the maximum flow. That is the reason we have written the method Edmund Cup, right? So here, before this method, we have written the same thing, max flow method, this method itself, right? So basically, we'll be making use of this particular method itself, right? So just give me a second here. we have to compute the minimum cut using the max flow, right? So I can just write it in this way, int flow equals, so let me call the max flow method here, right? So let me pass the parameters s, t as well as reachable. Yep, so this is fine. It's simple. Now we have to store the minimum cut value somewhere. For that, I'll be going with cut value of s. So nothing but I'll just assign this one to the low. I'll just assign this one to the low. Next, let's do one thing. Let's go with the for loop. Let's go with a simple for loop. I'll just go with for int I equals s plus 1, I less than v, and let me increment the I. Yeah, so this is fine. Within the for loop, what we will be doing, so if the vertex lies on the same side of the cut, then we have to change the parent. Yep. So for that, how can I write that one? Let me make use of the simple if condition here. If parent of I, so if it is equivalent to t, and so I'll just go with the reachable of I. Yeah, sorry. Yeah, so now if the vertex lies on the same side of the cut, then we have to change the parent, right? So how can I write that one? Let me write it over here itself. Parent of I, let me assign this one to the, right? So this is it. Let me come out of the for loop entirely. Now we will be adjusting the this one parent relationships. For that, let me write the simple if condition. Let me write this one quickly. Yeah, reachable of parent of nothing but t we have to pass. We have considered t itself, right? So within the if condition, so this one will be parent of s here, right? Let me assign this one to the parent of t. Yeah, I'll just go with the parent of t here. So this is fine. 1 second. Yeah. Next, let me go with the parent of t. So this one, let me assign this one to the s. Let me consider the cut value of s. So I'll just go with, let me assign this one to the cut value of t respectively. Then finally, I'll just go with the cut value of t. So let me assign this one to the flow, right? Just give me a second, 1 second. So let me do one thing. I'll just give flow here, right? So the error should be gone. Yeah. So this is fine. Now we are left with only one thing, nothing but considering the example within the main method. Yeah. So we are done with the algorithm actually. So I have already shown you the graph. The same example we have considered within the approach that I have shown you the graph, right? So we will be going with the same example. I'll not type the example part. I'll just copy paste that. We'll be considering that one within the main method. Yeah. Let's do that. Just give me a second. So this is it for the algorithm. So I'll just scroll this one. You can just have a look into it. Yep. So these are the global variables. So this is the BFS method, then max flow using the Edmund-Karp's algorithm actually. Yep. If you don't know Edmund-Karp's algorithm, you can just go through the 150 algorithms playlist and you can just watch the video and come back. Yeah. So it is used to find the maximum flow, right? So here we are finding the minimum cut. So we are building the tree and we are making use of the Edmund-Karp's as well as the BFS within here, right? So within the build tree. Yep. So this is it for the algo. Finally, let's consider the example within the main method. Let's do that. Just give me a second here. So usually I take the example part from the Google. So I'll just come here. Let me paste this one over here, right? So the same example that we had considered for the approach. I have considered the same thing so that it will be easier for us to understand. Yeah. So this is fine, I believe. 1 second. Just give me a second here. Yeah. Let me do one thing. I'll just remove this bracket. So not necessary. So yeah, let me format the code so that the code looks good. Yep. So now, yeah, let's do one thing. Let me run the code. Yeah, just give me a second here. Just run the code. Let's check whether we are getting the correct output. So I'll just elaborate this one. So see here, 0 to 1, we are getting the weight nothing but 4. From 0 to 2, we are getting weight equals 3. And from 1 to 3, we are getting the weight 5. Right? So we have already discussed this one. This is absolutely correct. So we are getting the correct output. Yeah. So this is fine, I believe. Now we are left with only one thing, nothing but discussing the complexity for the complexities for the algorithm that we have written, and later we can solve one problem by one problem with the same algorithm, yeah, from the code forces that we can do. For now, let's first discuss the complexities for the code that we have written. Let's do that. So here we are getting the wrong output, right? So we got 3 to 1 there while I was explaining the approach actually. This is not correct. Sorry. 0 to 1. So the flow is correct. Whatever accordingly with the code that we have written, we are getting in the correct way, but somewhere we have done something wrong. Might be in the maximum flow method. 1 second. Yeah, so here we are reducing actually, and here this line we are incrementing, right? So while explaining the code, I had said you the same thing, right? So instead of plus, I have given minus here. So this will cause everything wrong. So let me run this one again. This time I hope still we are getting the same output. 1 second. So let's do one thing. Before every BFS, this one iteration, this part actually, whatever we have written here. So let's reset the parent flow. Let's try the same. I'll just paste this one. Instead of that while loop, I have just added these two lines and I have changed the while to just true, right? So that's what I have done. So let me format the code and let me run this one. Still we are getting 435. We have to get 321, right? Why we are getting this one? Just give me a second. So what is happening here? So we don't have to scratch our head. So this can have the multiple outputs. So that is the reason we are getting this output. And 3 to 1 is also one of the correct outputs actually. Yeah. This is also one of the valid outputs. Yeah. So whatever that I have shown you during this one approach, that is also one of the valid output, right? So I got confused here. So this is fine. Let's stop here. We have got the correct output. This is the desired output that we have to get. This is one of the correct outputs as well. Yep. Now we are done with this part. Yeah, let's do one thing. Let's quickly discuss the complexities part. Let's do that. So what will be the time complexity here? Just give me a second here. Yeah, 1 second. Yeah. So what will be the time complexity? It would be big O of V minus 1 into max flow, right? For the max flow, I'll write MF. So why it is big of V minus 1 into max flow here? So this one, we are computing V minus 1 minimum cuts. Yeah. And also each minimum cut uses max flow, nothing but we are making use of the Edmond-Karp's algorithm to determine the max flow. So overall it would be big of V minus 1. Yeah. So each minimum cut uses max flow, and max flow I can just write it in this way. Max flow equals 0 big O of VE square. Yeah, max flow is nothing but big O of VE square. Now overall time complexity would lead to big O of V into VE square. Yeah, big O of V into VE square, right? So we can represent this part, whatever I have written, we can just represent this part. Finally I can just write it in this way because of V square E square. Yeah, overall time complexity would lead to because of V square and E square. So this is the time complexity. And what would be the space complexity here? Space complexity would lead to because of V square. So why it will be because of V square? See, the capacity matrix is nothing but V into V. We are going with the capacity matrix, right? So the capacity matrix would lead to because of V into V. And the residual graph is also V into V. Capacity matrix would lead to peak of V into V, and the residual graph, I'll just write RG here, that would be V into V respectively as well. And we are going with the parent and auxiliary arrays as well. That would lead to big of V, right? That would lead to big of V. So overall space complexity quite obviously would this one lead to big of V square, right? So this is it for the algorithm, and this is it for the complexities part actually. The time complexity and the space complexity for the code that we have written would lead to big O of V square E square and big O of V square respectively, right? So this is nothing but the time complexity and this is nothing but the space complexity. Yeah. So this is it for the time complexity and the space complexity part, and this is it for the algorithm. Yep. Let's do one thing now. Let's solve one problem from the Codeforces uh, using this particular algorithm itself, right? So Gomory-Hu tree. Let's do that. Yep. So let's continue here. So this is one of the problems where we can implement the Gomory-Hu tree, right? So this is one of the famous applications, we can say. Yep. So just give me a second. 1 second. Yeah. So here you can just go through the question. Yeah. It's not, I wouldn't say this is the simple one, but if you understand this one, you can solve this one easily. So that's what I would like to say. If you know the algorithm pretty well, you can just solve the problem easily. Yeah. So I can just go through the question. I'll just summarize the question so that it will be easier for us to solve the problem. That's what I will be doing. Yep. Just give me a second here. 1 second. Yeah. Yeah. First thing here, what does the question state? So we have n pumping stations. You can clearly see here. Yeah. We have n pumping stations connected with the pipes. So we have n this one pumping stations connected with the pipes basically, right? So bandwidth nothing but capacity. Just remember this one, bandwidth nothing but the capacity. Yep. So we have n pumping stations connected with the pipes having bandwidth nothing but the capacity. Each day, a guy named Mike chooses two stations, right? He can choose either of the two stations. One is VI. So here I can just represent this one, the two stations actually, VI to VI plus 1. Yeah. So we have n pumping stations connected to the pipes with the bandwidth capacity. Each day Mike chooses two stations, nothing but I represented this same actually, and pumps the maximum possible water. Pumps the maximum possible water, nothing but here in this case it is the max flow. Yeah. Here it is nothing but the max flow. Each day Mike chooses two stations, VI to VI plus 1, and pumps the maximum possible water, nothing but the maximum flow between them in 1 hour. In 1 hour. Just remember this one, in 1 hour, right? So then he must choose a permutation of the stations. Permutation of the stations is represented in this way, right? So not I actually, it is 1. V1, V2, V3, this one until Vn, right? So he must choose the permutation of stations V1 to Vn. His salary, Mike's salary, is equivalent to sum of max flow between consecutive stations, right? It is equivalent to sum of max flow, right? Between what? Between consecutive, this one, stations, right? So I'll just write here, consecutive stations. Yeah. Just give me a second here. Yeah. So just remember this one. Mike's salary is equivalent to sum of max flow between consecutive stations in that particular permutation. What we need to do then, right? So we have to find the permutation that maximizes the total flow. We need to find the, first of all, we need to find the permutation, right? So that maximizes what it has to maximize. We need to find the permutation that maximizes the total flow, right? That maximizes the total flow. I'll just write TF here, nothing but total flow, right? Again, we have n pumping stations connected with the pipes having the bandwidth, nothing but the capacity. Each day Mike chooses two stations, VI to VI plus 1. Yeah, that's how I represented, right? And the pumps the maximum possible water, nothing but the max flow. Yep. Between them in 1 hour. He must choose a permutation of stations, nothing but V1 to Vn, whatever I showed you, that one. He must choose a permutation of stations, V1 to Vn. His salary is equivalent to the sum of the maximum flow between consecutive stations in that permutation, in that particular permutation, right? So what we need to do, we must find the permutation that maximizes the total flow, right? That maximizes the total flow. Just give me a second here. Yeah. So this is the example that they have given here. Simple input. So this is the graph actually. The graph, I'll show you the graph within the problem, right? So you'll understand that one even better, right? Within the approach basically. Yep. So this is the output that we need to get. So that's what they have mentioned here, right? So there are 6 nodes they have strictly mentioned here and 11 edges. You can count here, right? So we have this one, what do we call? 6 nodes and 11 edges, and this one they have strictly mentioned here. 8, 9, 10, 11. You can just count here. And this is nothing but the first two numbers are nothing but edges. Yeah. U and V. Vertex U. This you can consider vertex V. This I'm just saying this one to understand this one better. Right. So Don't get confused. So this is nothing but the u, this is nothing but v, and this is nothing but the weight between the edges. Same goes with this one 168. So same goes for 168 and other edges as well. 16 is nothing but the weight. This one edges, edge 1 to 6, and 8 is nothing but the weight. So same goes with all the edges, right? 2 3 with a weight 4, edge 2 5 with a weight 2, and so on, right? So the output that we need to get here is 77. So the permutation that maximizes the this one total flow is nothing but here in this case 6 2 1 5 3 4 with a 77, right? With a 77. So this is what they have given in the question. So let's move on with the approach part, right? So I'll show you the this one graph so that we understand this one even better. So here, this is one of the famous what do we call? This is one of the well-known applications of the Gomory-Hu tree, where we can implement the Gomory-Hu tree correctly, right? So let's begin with the approach. Let's do that. So see, one thing I would like to tell you, let's discuss the key idea, then the important property of the Gomory-Hu tree, and then we can just this one get into the main part, right? So first thing, key idea is nothing but here, if we compute the maximum flow between every pair of nodes, it will be completely expensive, right? So we have to compute this one max flow between every pair of nodes that has been given, right? So that will be quite obviously this one expensive. So instead of that, so as we have discussed the Gomory-Hu tree, instead of that, we can go for the Gomory-Hu tree, right? So that's what we can do. Yep, let's move on with the important property here. So the Gomory-Hu tree, what it does, it stores the minimum cut between every pair of vertices. What it does again, just give me a second, 1 second here. This 1 second. Yeah, a Gomory-Hu tree. So what it does, it stores the minimum cut between the every pair of vertices using only n minus 1 maximum flow. So that's what we saw in the algorithm. So that's the huge optimization when it comes to maximum flow computations. Yeah, that is the only reason we make use of the Gomory-Hu tree, right? So we can just simply go for the this one, what do we call, Edmond curve or the Denix, right? So why we make use of the Gomory-Hu tree? Mainly due to the intense optimization, right? So again, a Gomory-Hu tree stores the what it stores minimum cut between every pair of vertices using only n minus 1 maximum flow computations, right? So then each edge in this particular tree represents, what does it represent? Minimum cut capacity between the partitions. What does it represent? Each edge in this particular tree represents the minimum cut capacity, right, between the partitions, right? Suppose if we cut the smallest edge, right? Suppose if we cut the smallest edge in the tree, right, repeatedly, we can build the optimal visiting order, right? So we can go on this one, cutting the smallest edge repeatedly in the tree so that we can build the this one optimal visiting order, right? So the salary becomes, so we have to this one uh, calculate the salary itself, right? So the salary becomes sum of the cuts used during the splitting, right? What does the salary become? The salary becomes sum of the cuts used during the splitting, right? So this is the graph, and don't get confused here. Edge labels is equivalent to the pipe bandwidth here, right? So 1 2 we have the weight 10, for 1 6 we have the weight 8, for the 6 5 we have the weight 2, and for the 5 4 we have the weight 7, 3 4 we have weight 5, and 2 3 4. For some this thing edges I have not mentioned, as I've said, this one edge labels is equivalent to the pipe bandwidth. Just I insist you to pause the video and have a look into it, right? The graph I'm speaking of mainly. Yeah, I insist you to just pause the video. Please pause the video and have a look into it. Yep, so this is fine. So this is the input, the same first this one first exam the same example that they have given in the question actually. So that's the input that we have considered here as well, right? So I can just look into the problem. Yeah, in the problem they have given the input, right? So the same example that I've considered here as well. So graph goes in this way. Yep. So I can just pause the video and have a look into it. Next, let's move on with the further things. So next step is building the Gomory-Hu tree, right? Instead of calculating each edge, we are building the Gomory-Hu tree, right? So here, what does this one building the Gomory-Hu tree? How does it help us actually? See, the algorithm repeatedly computes the maximum flow and the partitions. That's what we have seen in the algorithm as well, right? So the algorithm repeatedly computes the maximum flow and partitions. So example, see here, for the first step, we have 1 and 6, right? Max, we will be going with a 1 and 6. So we saw for every node how the parent was the source node in the algorithm. The same step we will be implementing here as well. So example here, the first step, maximum, we are going with a maximum flow of 1,6. Suppose minimum cut found is this one. Suppose capacity is equivalent to x, right? So this divides the graph into two partitions. We went with the two partitions itself in the algorithm as well. If you remember, we called that one two sets actually, one and first and second set, right? So every step we did the same thing. The same thing we will be doing here as well, right? So here this divides the graph into two partitions. So example partition, I have just shown you the example partition. So group A, we will be going with 1 to 5, and group B, we will be going with 3, 4, 6. 1 to 5, this one. Yeah. Group A, we will be going with 1 to 5, and group B, we will be going with 3, 4, 6. Yeah, this one. 3, 4, as well as 6. Yep. So here, right, so the example partition, group A will be 1 to 5 and group B will be 3, 4, 6. Then the tree edge is added. Yeah, then the tree edge is added. We are considering one, this one edge. For the first one we are considering, right, edge 1 to 6 actually. So this is nothing but the tree edge. Then the tree edge is added, right? So this is nothing but the weight. Then the algorithm, what it does, it recursively processes each group accordingly with the algorithm that we have written. Algorithm recursively processes, what does it process? Each group, right? After all steps we get a tree with n minus 1 edges. After all the steps we get a tree with n minus 1 edges, right? So now I have shown you the example Gomory-Hu tree, right? You can just look into the tree, right? So each edge weight is equivalent to the minimum cut between the two partitions. Again, let me repeat this one. Listen to this carefully. Each edge weight is equivalent to the minimum cut between the two partitions. See here, 1 to 2, we have the weight 10. 2 to 5, we have the weight 7. And here, 2 to 3, we have the weight 5. From 3 to 4, we have the weight 4. And 4 to 6, we have the weight 2. So the tree we can represent in this way, 5 to 2. So this is the first one, then 2 to 1, then already we have considered 2. So this will be 1 to this one 3, then 3 to 4 and 4 to 6, right? It will be 5 to 1, 3, 4, 6. Yep. So this will be again, let me write this one over here, 5 to 2, 2 to 1, 1 to 3, 3 to 4 and 4 to 6 respectively. Yep, so this is fine. So how the optimal permutation is found? We have to find the optimal permutation itself accordingly with the problem. Yeah, we have to find the optimal permutation itself accordingly with the problem. So now we cut the smallest edges first. Accordingly with the question, what we do, we cut the smallest edges first. Yep. So this whatever this one, we are going for the smallest edge, right? So that is done recursively. So now we cut the smallest edges first. This splits the tree recursively and builds the visiting order. That's what I said in simple terms, right? So we are making use of the recursion, and that splits the tree recursively and builds the visiting order, right? So the main idea is every cut contributes its weight once to salary, whatever the edge that we consider, right? Every cut that we make using recursion contributes its weight once to the salary. We have to find the max salary according to the cut itself, right? So every cut contributes its weight once to the salary. So total salary will be equivalent to the sum of the chosen cut weights, quite obviously, right? So the total salary will be equivalent to the sum of the chosen cut weight. So this is the approach that we will be going with. Yeah, this is the approach that we will be going with. Now we have discussed the question. We are done with the approach part as well. Let's write the code. After writing the code, we can just discuss the output and finally discuss the complexities part, right? So first, now as we have complete idea on the Gomory-Hu tree, let's do one thing. Let's start writing the code. Let's implement the same thing, right? Let's implement the Gomory-Hu tree algorithm. Um, yeah, let's implement it within the code. Let's do that. So let's do one thing. Let's start writing the code. First, let's go with the fast input output classes. I'll just go with import here, Java dot. I'll just go with input output dot start. So let me remove comma here, not necessary. And let's make use of the utility package as well. So I'll just go with import. So let me type here, right? So this is fine. Next, let's do one thing. I'll just go with the main. Yeah, main. So instead, let me make use of main. Yeah, so this is fine. I'll just remove this one. Public is not required here. So within the main class, what I'll be doing. So let's go with this one, global variables, right? Some of the global variables that we require. So I'll just go with static final here. So let me go with int n equals 210, right? So this is the maximum number of nodes, right? Accordingly with the constraint that I have considered, you can just go through the question. Yep. So I'll just go with the static here. Let me go with the final again int. Let me consider infinity. Yeah. I'll just go with 0 followed by 7f. 7f actually 4 times. Yeah. So I'll just go with this is fine, I believe. 1 second. Yep. This is fine, I believe. Next, what am I going to do? So we have to go with n stations and m pipes. Accordingly with the question, we have n stations and m pipes, right? For that, I'll just go with, sorry, let me go with a static, yeah, in n and m, nothing but stations as well as the pipes. Next, let me go with, I'll just go with the static here, int. So let me go with a equals size new int of n. So this one is nothing but we are going with the array, right? Array storing the station permutation, right? So this is fine. Let next what shall we do? So let's go with the edge counter for the Dinitz graph, right? So I'll just go with the this one static. See, one more thing I want to tell you. In the algorithm, we have made use of the Edmond curve. So here I'm making use of the Dinitz as Dinitz is somewhat easier to implement, right? Rather than Edmond's curve, right? So you can just go with the Edmond's curve as well. It doesn't matter. So if you don't know Dinitz or Edmond curve, so we have already discussed that one and it is present in the 150 algorithms playlist. You can just go through that and you can come back here, right? So I'll just go with end. So let me go with total. Let me initialize this one with a 1, right? So this is fine. Yep. So this is nothing but the edge counter for the Dinitz graph. Next, we need the array for the adjacent cells, right? So for that, I'll just go with a static here int. I'll just go with h equals new int of n. So this is fine, I believe. Next, let me go with static. So this one is int. I'll just consider the temp here. So this one will be new. Let me go with int. So I'll just go with this one. This is nothing but the backup capacities, right? So I'll just go with 1 followed by 4 zeros and 1 0, right? Don't get confused here. This is nothing but the backup capacities. Next, what shall I do? I'll just go with the edge class. So I'll just go with static class edge. So this is fine. Yep. So within the edge class, I'll just go with int v w. So I'll just go with the next here, right? So this is also fine. Yep. So v is nothing but the destination. W is nothing but the capacity, and nxt whatever I have given, nxt is nothing but the next edge, right? So here let's go with the constructor edge, right? So I don't have to go with anything here. So I'll just leave as it is. Yep. So this is fine. Yep. Now let's go with the main constructor. So I'll just go with edge here. So this one will be int v. So let me go with the weight as well. Let me go with the next this one. Weight is nothing but the capacity. Let me go with the next edge as well. Right. I'll just type here and next. So here let's initialize quickly. V equals v and capacity nothing but w equals w. And finally, we have to go with the link to the next edge as well. So I'll just go with the nxt equals. Yep. So this is fine. I'll just come out of this one entirely. Now we need the Dinic edge list. For that, let me go with the static edge. So this is fine. E equals new edge of let me copy paste the same thing. So this one. So I'll just copy the same thing and let me paste it over here, right? So this is fine. So this is nothing but the Dinit's edge list. Next, let's go with a helper method add. So I'll just go with static here. Let me go with a void add. So I need certain parameters, edge, nothing but u and v, vertex u and v respectively, and wait. For that, I'll just consider w. It's simple, right? First, let's go with the destination capacity as well as the next pointer. It's simple, very simple. So I'll just go with plus plus. We have considered total TOT, right? So I'll just go with dot v, that is equivalent to v, right? So this is fine. Next, what I'll do, I'll just go with the e of, again, let me consider TOT here. So dot w, let me assign this one to w again. So same thing, e of this one, well, so I'll just go with the next e equals h of u, right? So this is fine. So we have went with the destination capacity as well as the next pointer. Next, we need the head to update, and also we have to save the original capacity. These two things we need, right? For the for updating the head, I'll just go with a h of u, that is equivalent to total. So this is fine. And let me go with the temp of this one, total. So this one, yeah. So I'll just assign this one to the w. Yep, so this is fine. I'll just come out of this one entirely. Now we need the level array, or the just array for the BFS. Level array means we have to save, we'll be saving level by level, right? Within the BFS. So we need the level array for BFS. So I'll just go with static here. Int e equals new int of size n respectively. Yeah. So next what I'll do, let me go with a Boolean. I'll just go with BFS here, right? So this is one more helper method that we'll be making use of. So I'll just go with the two parameters. One is s and another one is, yep. So this is fine within this particular method. So let me leave space here so that we understand this one even better. So within this method, first thing we have to initialize the levels as we are making use of the BFS. So I'll just go with arrays dot fill. So let's fill the D initially with the infinity. Yeah, so this is fine. Next, let's go with the array DQ, right? So I'll just make use of the array DQ here. So I'll just go with integer, right? Let me go with the integer. So let's continue with the same. I'll just go with the integer here, right? So this is fine. So we are making use of the array DQ, right? So I'll just make use of the variable q here, and this one will be new array DQ. Yep, so this is fine. Next, what we are going to do, let's start the BFS from the source, and also we have to consider the level of the source. These two things we have to do. First, let's start the BFS from the source. For that, I'll just go with q.add of s, and then we have to go with the level of source, nothing but d of s. Let me assign this one to the 1. Yep. Now, let's move on with the further things, nothing but while loop. So I'll just go with the while here, and not of q dot is empty. So this is fine. So within the while loop, what we'll be doing, let's consider the current node, nothing but here, int u equals q dot poll. This one is fine. Yep. So let me go with a simple for loop here for int I equals h of u. So this is fine. I not equal to 0. So this is also fine. Let me assign I to e of I dot next, right? So this will be incrementing as next is nothing but the next edge. Yep. So this is fine. Somewhere I did something wrong. Why I have to close this one here? H of u, I have to close this one here itself, right? So this is fine. So now, yep, within the for loop, what we will be doing. So I'll just assign v to e of I here dot. It's simple. Now I'll just write the simple if condition. If e of I, right? If e of I dot w, if it is not equal to 0, 1 second. If it is not equal to 0, and we have to consider here this one, d of v, if it is equal to infinity, nothing but inf here. So then what we'll do, I'll just go with d of v equals d of u less 1. So this is fine. Next, finally, what we'll do, so we have successfully assigned the level and we are pushing that one to the queue, nothing but I'll just go with a q dot add of v, q dot add of v, nothing but we have successfully pushed to the queue. So this is fine. So I'll just come out of this one entirely. Now we have to return if the sync is reachable, right? So I'll just give return here. So d of t, we have to return only when the sync is available or reachable. Sorry. Yep. So I'll just write here if d of t not equal to infinity, right? INF. This. So this is fine. This is it for this particular method. Nothing but BFS method. Yeah. I'll just come out of this one entirely now. Right. So next, as I've said, we'll not be making use of the Edmonds cup. Instead, we'll be going with the Dinitz algorithm. Let's go with the Dinitz algorithm. So I'll just go with static here. Int, I'll just go with the dinic. So I need certain parameters, edge, nothing but the vertex u, vertex v, as well as I need the flow. We will be calculating the flow itself, right, by making use of the Dinitz algorithm. So even if we would have made use of the Edmonds cup, also we would have we should be calculating the flow itself, right, or we would have calculated flow itself, right. So let me go with the parameter flow. So first thing, if we have reached sync, so I'll just go with if u equals t or flow equals 0, then in that case we have to return what we have to return. We have to return flow. Yep. Next, I'll just assign rest to flow. Yep. So this is fine. Next, let me go with a for loop. So I'll just go with int I equals h of u. So then I not equal to 0, and let me go with rest greater than 0. Sorry, greater than 0. I equals e of I dot next. Yeah, I would have copy pasted and made the necessary changes. Anyways, so let me go with int v equals e of I dot v. Yep, so this is fine. Next, let me write the simple if condition here. So if e of I, h we have considered e itself, right? So just go with 1 second. So e of I dot w. So this one not equal to 0, yeah, not equal to 0, and d of v, it is equivalent to d of u plus 1. So I'll just go with int k equals, so let me call the dinic. As I've said, we will be this one recursing, right? So I'll just call the dinic itself. Dinic here, the parameters that I need to pass actually, vertex v, t, as well as I'll just go with, we have to find the minimum, right? So I'll just make use of the math.min of e of I dot w, and let me go with the rest here, right? Let me go with the rest. So suppose if k equals 0, in that case, I'll just assign d of v to infinity. Yeah, it shouldn't. Suppose if it exists, then I'll just assign this one to infinity. Now we have to reduce the remaining flow, reduce the capacity, and add the reverse flow, right? If you know that in its algorithm. So I'll just reduce the remaining flow here. Rest equals rest minus k. So I'll just go with k. And then we have to reduce the capacity. I'll just go with e of I dot w. So let me assign this one to k. And finally, we have to add the reverse flow, nothing but e of I to the power of 1 dot w equals the same thing plus k. Yep. So next, I'll just come out of this one entirely. Now all we have to do is we have to return the pushed flow. For that, I'll just go with return. So let me go with the return. I'll just call the flow rest actually. Yep. So let me go with the flow rest. Yep. So this is fine. We are done with this part. Yeah, I'll just come out of this method entirely. Now, let's move on with the further things. Yeah, I'll just go with a static. So we have to build a tree. This one, what do we call? Gomory-Hu tree, right? So the same. We are implementing the same algorithm. So I'll just go with to build the tree initially. I'll just go with a node here. So I need two parameters. One is v and another one is w. Right. So let me go with the capital ones for both. Right. So this is fine, I believe. Let me go with the constructor part here. So this one will be v and this one will be weight w. Right. So within the node, first thing, we have to go with the neighbor as well as the cut weight. So I'll just go with this dot v equals v. This is fine. and this dot w equals w. So this is also fine. I'll just come out of this one entirely. First thing, we have to go with the Gomory-Hu tree itself, right? So I'll just go with the static here, right? So let me go with list. Within the list, let me pass node. That is the reason we have went with the node earlier. So this one will be G. I'll just go with new array list. Yeah. So this is fine of size n. Yep. So next, let's go with a add method. So I'll just go with a static here, void. So let me go with add, right? Add e. So we need three parameters, edge as well as the weight, int u, w as well as weight, nothing but w. Yep. So we have to add the edge in the tree. For that, I'll just go with a g of u dot add of, let me go with new node. Yep, node. I'll just pass v and w respectively, right? So after successfully adding the edge in the tree, next we have to build the tree. For that, I'll just go with a static void. So let me go with build. Yep, let me go with a build here. So I need two parameters. One is left, another one is right, L and R respectively, right? So within the build method, first thing, the base case. So suppose if the left is greater than or equal to right, then we don't have to return anything, right? So I'll just go with if left greater than or equal to, sorry, greater than or equal to right. In that case, I'll just give return. Yeah. The next step would be we need the result variable. We have to store the result somewhere. So we need the result variable quite obviously. So I'll just assign result to 0. So this is fine. Next, let me go with a while condition here. So let me call the BFS method that we have already written. Yep. So I'll just go with a of left. Let me go with right as well. Right. So this is fine. Yep. In that case, we have to compute the maximum flow. I'll just give result equals result plus, let me call the denic method that we have already written. So this will be denic of a of L, comma, a of R as well as infinity. For the infinity, I'll just go with INF. The variable we have made use of INF itself, right? Earlier. So I'll just call that one here. So after successfully computing the maximum flow, then what we will do? So we have to add the tree edge. For adding the tree edge, I'll just go with a add e. So we are making use of this method, this particular method, right? So I'll just if you not just add, it is add e, right? So this is fine. For adding that, how can I write that one? So I'll just go with a of L here, as well as right part as well a of R and result, right? So let me copy the same thing here. So let me copy the same thing. Let me paste it over here. Right. So what we are doing here, a of this one will be right. So this one will be a of left, and this one is result. So this is fine. We after successfully adding the tree edge. So what we have to do, I'll just go with the integer here. This one integer. I'll make use of the variable a double r, nothing but the array. So this one will be new integer of r minus L plus 1. It's as simple as that. Now let's move on with the for loop. So for loop, I'll just go with for int I equals 0, say less than length of the array, nothing but array dot length. Then finally, I'll just increment the I. So within the for loop, what we have to do within the for loop. So let's do one thing. I'll just go with array of I. Let me assign this one to array of this one. I'll just go with a L plus I. L plus I. It's as simple as that, right? So next we have to go with a partition by the BFS level, right? So I'll just go with arrays dot sort here, right? Arrays dot sort of, let me go with array comma x comma y here. So this is fine. I'll just go with d of x minus d of y. So this we are going with a partition by the BFS level, right? So this is fine, I believe. Next, let's go with a simple for loop. So this one will be int I equals 0, I less than length of the array. So next, finally, we'll go with a I plus plus, nothing but this one, I plus plus. Then a of, I'll just go with a L plus I here. Let me assign this one to the array of I. Yep, so this is fine. Next, we have to go with the minimum cut, right? So initially, let me assign cut equals 0 here, and let's move on with the for loop. So this one will be int I equals L, I less than or equal to R, and let me increment the I. So let me write the simple if condition here. If D of what? If D of A of I, so again this one, if it is equivalent to infinity, right? If it is equivalent to infinity, so sorry, yeah. If it is equivalent to infinity, then what we have to do? I'll just go with the. I mean, we have to find the partition point, right? For that, let me assign the cut to I here, and let me give break, and let me give break here, right? So this is fine. I'll just come out of this one entirely. Now let's go with one more for loop. So this one I'll just go with int I equals 1, I less than or equal to total. Just go with the TOT here. Let me increment the I. So within the for loop, let me do one thing. We have to restore the capacities. For restoring the capacities, I'll just go with the E of I dot W. So I'll just assign this one to, we have considered for the temp, I have went with the TMP, right? Temp of. So let me go with the I. So next we have to build the left and right subtree. For that, I'll just go with a build. So 1 second, we are recursing right here. Yeah, we are recursing itself. I'll just go with a build of L, comma, let me go with cut minus 1. So this is fine. Again, we have to build the right subtree. For building the right subtree, I'll just go with a build cut, comma, R. Right. So this is fine. Next, let me come out of this one entirely. Now, let me go with, sorry, not this. Let me go with a static here. Did I do anything wrong? No, right? So let's go with certain variables here. Int, I'll just go with a right tree 1, right tree 2, as well as value. And let me go with a count. And one more thing, let me go with the answer. And we have already made use of the result variable, I believe. I'll just go with the answer itself. Anyways, so let me go with one more variable. Why this is like this one? Yeah. Let me go with the static here. So this is fine. 1 second. Yeah. Static. So I'll just go with the int here. So this one will be result equals new int of, I'll just go with the size n. Yep, so this is fine. Next, we will be making use of the hash set. So I'll just go with static here, hash set. So this one, I'll just go with the long. Yep. Let me go with s here. Yep. Variable name. Let me consider new hash set. Yeah. So next, we are left with certain this thing. 3 methods actually. One is we have to go with the DFS. So we'll be performing the DFS and we'll be solving. So one more thing is we have to, just give me a second here. We have to combine the two ints into the long. For that, we'll be making use of the pair, right? These 3 things we will be doing. Let's do that. First, let's do one thing. Let's combine the two ints into long by making use of the pair method. So I'll just go with the static here, right? Long pair. So this is fine. I need 2 parameters. One is A and another one is B. Right. So finally, what I'll do, I'll just return what I need to return here. I'll just give long. So this is fine. Let me give A. This is also fine. We are combining the two ints into long, right? So I'll just make use of the left shift operator here. 32. Logical or B, right? Logical or B. So this is fine, I believe. Why? What happened here? 1 second, just give me a second here. So let's continue with the same. This is it for the pair method actually. I'll just come out of it and let's go with the DFS method. Yeah, I'll just go with static here, Boolean. So let me go with the DFS. So this is fine. Let me go with 2 parameters. One is U and another one is FA, right? So this is fine. Within the DFS method, first thing I'll just go with the leaf node. Let me consider the leaf variable and set this one to the Boolean value true. So this is fine. Next, let's go with a simple for loop. So I'll just go with this one node to of g of u, vertex u. Right. So within the for loop, first thing, if let me write the simple if condition as we are dealing with a DFS. So I'll just go with a 2 dot if it is equal to fa, the parameter that we have considered within the method, I'll just go with s dot. Let me go with the contains, or let me go with the contains itself, right? Contains of, let me call the pair method. Yep. So pair, I'll just go with u, comma, u dot b. Right. So this is fine, I believe. Next, in that case, we have to skip. So I'll just make use of the continue keyword. Next, let me go with a simple if condition. One more if condition here. If 2 dot w here, if it is less than value, then what I'll do, p and w, 1 second, if we have considered. So this one I have missed the bracket somewhere. Actually. I have misplaced the bracket somewhere. We can just this one, the global variables, right? 1 second. Anyways, so let's do one thing. Yeah, let's continue, and I'll just let's debug that one later, right? So I'll just go with a value. Yeah. So let me do one thing. Yeah, within this one, we have to find the smallest edge. For that, I'll just this one assign the value to 2 dot w and write tree 1 to u, and finally rt2, nothing but the right tree 2. Let me assign this one to 2 dot b. Yep, so this is fine, I believe. I'll just come out of this one entirely. Let me call the DFS method here. 2 dot this one v, comma u. Right, so this is fine. I'll just assign the leaf to false actually. Yep, so this is fine. Finally, what we'll do, let me return leaf. Yeah, let me return leaf. Yep. So this is fine. So this is it for the DFS. We are left with only one thing, nothing but we have to mm, we are left with we have considered left and right? So we have to solve both sides. Yep. So for that, I'll just go with one more thing, one more method actually. I'll just go with static here. So this is the problem of the this one. I have misplaced the bracket. Anyways, I'll just go with void. So let me go with solve. So I need only one parameter, nothing but edge, right? So here in this case, value, let me assign this one to infinity. So this is fine. And let me go with a simple if condition here. Let me call the DFS method. So DFS of what? DFS of u, we are starting from the 0, right? So this is fine. Within the if condition, we have to add to the permutation. For adding that one to the permutation, I'll just go with the count here, right? So let me assign this one to the u, and let me hit the return. Yep, so this is fine. I'll just come out of this one entirely. Now we have to mark the edge that we have removed. So I'll just go with the s dot add of pair. Pair, I'll just go with right tree 1 and rt2. So this is fine. Yep. Now the same thing I'm gonna do again, right? So just change this one. That's it. Swap this one. Let me copy this one and paste it over here, and I'll just go with the 2 and 1 here. Right? So this is the only change that we need. Yep, so this is fine. We have to add this one, cut weight to the answer. For that, I'll just go with the answer variable. We have went with ANS. I'll just go with this one plus value. So this is fine. Let me go with int tx equals rt1, and also let me go with int ty equals rt2. Yep, so this is also fine. Finally, we have to solve the first part and we have to solve the second part as well. For solving the first part, I'll just go with the solve of tx, and for solving the second part, I'll just go with the solve of ty. Yep. So this is it for the code actually. So this is it for the code. This is fine. We are left with only main method. So that's completely related to the input output part. So I'll just copy paste that one. Yeah, just give me a second. So here I have given capital V and W. I'll change this one to small v and W. So this is fine. Mm, So here I have pasted the code actually. So one more thing, I had given one extra this one flower braces actually. If you are following, you can just remove that one. So I had given one extra, so that is the reason it was giving me error, right? So I have removed that one. Everything works fine now, right? So this part I have copy pasted, right? So this part I have copy pasted main method mainly. So what does it do? So this one buffer data and print writer is completely related to the input output. This one also I don't have to explain. So this one, let's come to the forward edge as well as the reverse edge. So we have made use of the add method here twice. So we have called u, v and w, nothing but edge u and v. Uh, Edge or the vertex u and v respectively, and this one w is nothing but the weight, right? So we are adding the forward edge as well as we are adding the reverse edge. These two things we are doing. So this is fine, I believe. Next, let me come to the build part where I have called the build here, build method. So build, so we are constructing the Gomory-Hu tree. So that's what we are doing, right? So this is one of the problems that I have found that where we can where we have to implement the Gomory-Hu tree, right? So this is one of the wonderful applications of making use of this one Gomory-Hu tree algorithm. Next, let me go with the solve. This solve method actually, we are computing the best permutation here by making use of the solve, right? So this is fine. So this is it for the coding part. Yep. So this is it for the coding part. I have explained you step by step. Now I don't think I have to explain this one again, right? So yeah, let me run the code. Let's see whether we get the desired output or not. So I'll just come here. Let me run this one. Yeah. So let's copy paste the same thing, right? So the input that we have. So we are going with the buffer data and the this one print writer, right? So we have to provide the input here. Just give me a second here. So yeah, I'll just go to the Chrome. So let me copy the this one example or the input one. So we have to get the output this one, right? Yep. Let's check the same. The maximum salary the guy has to get, and these days actually, these are the notes of the day. So let's do one thing. Mm, just one and let me paste this one. Yeah. Here you can clearly see. If you are not able to see, let me maximize this one. Yeah, you can clearly see the output 77 followed by 6 1 2 5 3 4. So this 1 2 3 this one 5 4. So this one order doesn't matter here. We are getting the desired output itself. Yeah, we are getting the desired output itself. So we have discussed this one already. So let me minimize this one and let me do one thing. Let me copy this one entirely. Yeah. So let me copy this one entirely. I hope this works actually. We are getting the desired output. As I've said, let me copy this one entirely. And now, one second. What did I do? Anyways, just give me a second. One second. Yeah. Let me copy this one. And yeah, I'll just come to the Chrome. So let me hit the submit code button here. Let me choose this one E here and let me paste this one over here and hit the submit button. So one second. What happened here? One second. I think this error indicates that we have to go with a public class, I think. I don't know. Let me give here because I cannot give public here while I go with IntelliJ. So I'll just go with public. This is fine. P has to be small, right? So yeah. Now if I hit the submit button, yeah, this works actually. Let's wait for some time. I hope this is correct one. Lengthy code actually. I don't want to type this one again. Hope this works correct. Let's see. Let's wait for some time. So I can clearly see here, right? So we are getting the verdict accepted, right? So we have got the verdict accepted, right? So yeah, you can clearly see here, right? So whatever the code that we have written works absolutely correct. Now I hope this one Gomory-Hu tree algorithm is completely clear. So we have solved one problem from the Codeforces as well, right? I hope it is completely clear, right? So next, what we'll be doing, we will be discussing on the topic Stoya-Wagner global minimum cut. Yep. So it's somewhat similar to this one itself, not entirely, but if you know this concept, it will be somewhat easy, right? So these are the complex algorithms itself. So these are not the easy algorithms. These are complex algorithms itself, right? It will be somewhat difficult to implement. Yep. You have to know the algorithms pretty well if you want to implement this. Yep. So this is fine. So I hope uh, we are completely done with the this one. What do we call? Gomory-Hu tree algorithm and the problem that we have solved as well, right? So for now, this is it. Thanks for watching, guys.